in a trade, especially in the food trade. So when you have a scales, that the range of these scales actually this is a spring scale, or they have some levers. See, not springs, they have some levers inside, counterweights inside, which are actually hidden inside the body of the scale, and the lever system with the counterweights is designed to be able to indicate the weight from 0 up to 1 kilogram with masses. So measured masses from 1 to 0 kilograms, and this indication is used by means of index. So actually, this scale show what the weight is, but up to 1 kilo. If the weight is bigger than 1 kilo, greater than 1 kilo, so we have to add some counterweights on the opposite part of the scale, and then the scales, in fact, show the readout of the scale. It's a difference between the weight of the object and the counterweight. So if I put here 1.5 kilo and put here 1 kilo counterweight, my scale show me half a kilo. So it shows a difference between mass of the object put on this part of the scale and mass of the counterweight part of this part of the scale. So if this mass is 0, it just will be the mass of the measured mass of my object. So this is the two examples, so zeroing and differential measurement. We are actually more interested in electrical measurement than in mechanical, but nevertheless, so this is just an illustration. Even with such zero method, we may introduce another, so for such kind of scale, so when we actually weight something, try to weight some mass, let's imagine that we trade, I don't know, gold or something else, yeah? So we actually put our object on one scale, one part of the scale, and add these counterweights until the scale will be balanced. But the question is whether the fact that scales are balanced indeed means that mass of my object is equal to the mass of all the counterweight. Is there any errors possible? And what may be the source of this error? So given what may be the source of such a error? Two halves of the scale may have a different masses, but more important that if they have a different masses, we see it immediately. But more important that they may have a different length. And if they have a different length, that means if the side when we put our counterweights is longer, a little bit, than its counterpart, so then actually to balance the scale, we have to put less mass of the counterweights than that is actual mass of our object. And by this we may actually cheat sometimes, yeah, to making the scale not equal. Well, and sometimes some people was caught for such a cheating. They make wrong scale. But even if we have a wrong scale, we may design such a measurement method that allow us to neglect or to compensate for such a difference in scale, for some such a wrong or incorrect scale. And this is a method what is named as replacement method. For the replacement method, what do we need? So we still have our comparison. We still have our comparison device. We have some indicator, but we need to have some memory element. So how we actually works? So we connect our we put actually our measured value first. We put a measured value to the input of the, yes, it's actually correct for these two switch. Let's imagine the switch 1 is closed and switch 2 is closed. So I actually take, yes, switch 1, switch 2. So I put my input value on the one of the inputs, or input value on the input of my comparison device, but the second input is connected with this memory element, and then I regulate the memory element until I get the balanced output. So I use here a zero method. So I add this memory, I change the value of memory element to balance the scales. Then I switch from my signal to some reference source of the signal and start to balance once more, but now I change not a memory element, but I change the reference source, parameters of reference source. And I try to balance once more my comparing device, balances back to zero once more, with now changing not a memory element, but changing this reference source. And when I get this balanced, what may I state about the value of this reference source that this reference source produced? So the scale was in balance when I put my unknown value x in, and I made it in balance. Now I remove my input value and add reference value. And one more, I actually lead my device to balance back. So it means that the value which is on the input here in the first case and in the second case should be equal. Because in the first case it was balanced, and now with adjusted reference elements is balanced too. It means that the current state of the reference elements, the current signal that my reference elements produce, is equal to my input signal. So, and this actually the principle of this replacement method. And this replacement method actually doesn't, now it's not so important how accurately work my comparison element and how accurate is memory element. It's enough. It's absolutely not important. If I has it in balance with my measured signal, and now I have it in balance with my reference signal, it means that both reference signals and measured signals are equal. So here is example how to do it in a weighting. So if I going to weight some object, I'm going to weight some object, what will I do? So I put my object on a scale. I can imagine that my scale may be absolutely incorrect. I may take even, I don't know, I may take even some kind of rod, attach two plastic bags to the sides of the road and hang it on some rope in the middle. So they will be absolutely inaccurate. But if I have an accurate counterweight, what should I do? So I put my object on one side of the scale, and I have to add some arbitrary thing as a counterweight. I may use, for instance, sand. In real manual measurement, sand is used very often because you may provide a dose of your sand very accurately to dose your sand by grain by grain. So you actually, and I put something on the other part of the scale to balance them. Then I remove my measured object and start to add weights, calibrated weights, until I got my scale balanced once more. And it means that I even not care about the mass of the sand because of differences in these levels. My mass of the sand may be different from mass of my object, but this replacement method allow me estimate this mass. But if in this situation I have a balance, and in this situation I have a balance, and amount of sand doesn't change, it means that mass of all the weights of the counterweights that's used is equal to the mass of my object. So I got a correct number. So this is just an example of what the comparison method means. Okay, we may take a small break now, I guess. Yeah. No. Still 5 minutes. Well, so And now let's turn to the circuits which are used in electrical measurement, more or less. So we started from a bridge circuit. So we discussed DC-AC bridge. We discussed what does a balanced bridge and imbalanced bridge mean. Some different type of the bridge, consider some different type of the bridge, and finally we discuss what is an automated bridge, how they may be automated, and what we could measure with such a bridges. We speak here in this lecture, and this generally this course, about only one type of the bridge, which is probably most useful, is used most often, and I would say it's perfect for the DC measurement. So it's so-called Wheatstone bridge. If we look at the so this is a circuit of the Wheatstone bridge, designed for the operation. I would say it's more designed in such a way. It's more designed in operation in a differential mode than in a balanced mode. But still, so if you're actually looking at the bridge, why such kind of circuits is named as a bridge? So here we have some power supply. So we add plus here, minus or ground here. So we have a voltage applied between this and this point. And if you look at this bridge, we actually find a 2 voltage divider. So the resistors R1 and R2 form a 1 voltage divider, and R3 and R4 form a 2nd voltage divider. Generally, we very well know what to do with the voltage divider already. But the outputs of this voltage divider is connected with some measurement device. So here I put a voltmeter between them. It could be an ammeter here too, but here is with a voltmeter. So this actually connection between output of the one divider and another divider. So this it looks like a bridge between two coasts. So in one lane in the second lane, and there is a bridge between two lanes. Yeah? So that's why these circuits are named as a bridge, because this is like a bridge between two sides of the river. To operate in a balance. So if we look at this, we say that the bridge is in balance. The bridge is balanced when this voltage between these 2 points over the bridge, the voltage over the bridge is 0. When it will be? It will be when the voltage in a point 2. So if I look at this circuit as an electronic circuit and measure all my voltages in respect to the common point or to the ground. So the voltage in the point 1 should be equal to the voltage in the point 2. So in a balance, so these voltages are perfectly equal. So the difference is voltage or voltage U12 between these 2 points is equal to 0. Therefore, even the resistance of the voltmeter is very low. Even I replace this voltmeter just with a wire. So the current through this wire will be 0. So this is a bridge balance rule, a bridge balance condition. So when this voltage is 0, we say that the bridge is balanced. How to estimate how could we design these balance rules? So it's quite easily to understand. So let's look at the let's try to describe. Let's try to describe. Yeah, let's try to describe it. So if these voltages are equal, yeah, both these resistors Rx and R2 and R4 are connected to ground. So, and if we have a two current I2 that flow through the resistor R2 and current I4 that flow through the resistor R4, so the voltages over these resistors will be just current times resistance. So I2 R2, it's a voltage over the resistor R2, and this is actually a voltage in this point. I4 R4, it's a voltage in the point 2 here, and these voltages should be equal. So this is the first equation that we could derive from this circuit. Another equation in the same way. So if these voltages are equal, so we should take into account. So this voltage will be equal to the power voltage UB, which I've applied here, minus voltage which is dropped over the resistor R3 or Rx. So if we imagine that currents which flow through resistor R1 is Rx is 1, R3 is I3, so then we may express these voltages over this resistor and this resistor, like I1 Rx and I3 R3, and they should be equal to. They couldn't be different. So these two should be equal, voltages should be equal, and these two should be voltages should be equal. That's in this way, these voltages should be equal to. Well, okay, or difference will be 0. Okay, now because the current through this I1 and through this bridge from point 1 to 2 is 0 in balance, it means that the current I1 couldn't flow to the point 2. It could flow only through point 1 into resistor R3. It means that current I1 and I2 is equal. This current equal to this current. And the same idea, I3 could not branch into point 1. It should go through point 2 and further in point 4, because in a balance, current here is 0 between 1 and 2. So it means I3 should be equal to I4. So I3 is equal to I4. Taking these two equations and dividing it one by another, and bearing in mind that I1 equal to I2 and I3 equal to I4, we will get this relationship between resistances R1, R2, R3, and R4. So the ratio between resistors here and here should be equal to the ratio between resistors here and here. How could we use it now for the measurement? So let's imagine that we have an unknown resistor instead of R1. We don't know the resistance of Rx. So I put it here and I see that there is some voltage. What should I do? I should now take some reference resistor, and very well to have a changeable reference resistor, and I'll put this reference resistor instead of R3, and I regulate it until I get voltage, 0 voltage here. And then, knowing R2, R3, and R4, I may calculate my Rx. In practice, I may take R2 and R4 equal. If R2 and R4 are equal, then my balance will be enforced. My bridge become balanced, where R3 will be exactly equal to R4. And then I get, well, when I get my bridge balanced, I mean I get a voltage 0 here. I may be pretty sure, okay, and now my resistor R3 is equal to Rx. And by this way, I measure my Rx. Practical circuit may be a little bit different from the scheme I just described. It. Why? Because first of all, the voltmeter may have not enough sensitivity for the difference in voltage difference between point 1 and 2. That's why very often the device in analog bridges, the device which actually measure voltage or current through the bridge, the current which flow from 1 to 2 or back, it's often is ammeter. The ammeter is a smaller resistance, but very often we have a possibility to connect some resistance in series with an ammeter to make the measurement more rough. And this is usually so-called sensitivity control. So first we connect this additional resistors. We actually turn a little bit this ammeter into voltmeter and measure this voltage until we get it as close to 0 as possible. Then we turn it to ammeter and adjust even more, because the ammeter generally is more sensitive to the small teeny change in voltage between 1 and 2. And then we use an ammeter. For instance, it may be some kind of even micro ammeter, to measure very, very teeny currents. Well, and usually we have one balance. We have a one balance resistor, or it's even, we see in the future, it's even not a single resistor. They call it reference resistance, and very often they are made in the form of the resistor box. So we use a resistor box to, instead of this alternating resistor, and we change it resistor until we get a balanced bridge. But often these resistor boxes, are manufactured with a limited range of resistivities. For example, this box what we have in our lab. It's quite old, but it's limited in his resistance. It's limited, if I remember correctly, up to 10 kilo. So it's 0.123. Yes, it's nearly, yes, it's from 0 up to, so it's ohms, it tends up to, yeah, up to 10 kilo ohms. Yes, it provided 10 kilo ohms as a maximal. So if we're going to measure something bigger than some resistance which is bigger than one with 10 kilo ohms, it will not be enough to have such kind of box. What to do? And we may actually use a possibility to scale measurement with a bridge. So we discussed this example when Rx equal to R3, both these resistance R2 and R4 are equal. So if I look at this equation, I'll easily understand that my Rx is equal to R3 times R2 divided by R4. So if I take R2 and R4 equal, I get Rx are equal to R3. If I take, for instance, R2 times R4 10 times higher than R2, I will get that Rx will be 10 or 10 times lower, sorry, 10 times lower than R2. I will get that Rx is 10 times higher than R3. So, and by changing these resistors, I actually may change a range. Yeah, so I take this R4, yeah, 10 times higher. For instance, if I going to increase my range, comparing with the maximal value of the R3, with the R3 is up to 10 kilo ohms, I want to make up to 1 mega ohm, for instance. So I will take, or up to 10 mega ohms. So I will take this R4 1000 times less than R2. And in this way, yeah, I make my Rx, which balance, yeah, my yes, the Rx R3 that balance my Rx, yeah, it will be maybe 3 times 1000 times lower, 3 order lower than Rx. If I need to measure lower resistances, yeah, then minimal R3 allow, or with a higher accuracy to use all the range of R3. So I take this resistor R4 higher than R2, for instance, 10 times higher, 1000 times higher. So by this, I may change the range of my resistance measurement, having limited range of my resistor box, what I use for the balancing. About the resistor box itself, so as I said, yes, this is devices. This is actually what these resistor box are. It's actually some kind of work ethelons or measures. Yeah? And these work ethelons, they usually are of very good accuracy class. Accuracy class maybe 01 or 2, what means that the set resistance is the accuracy of set resistance doesn't exceed 0.1% of the set resistance. So it's not so bad. Yeah, and they are actually designed as a series of resistors. They connected in series. For instance, this is a resistors, each of one is 1 ohm. Here is a resistor which each of one, for instance, is 10 ohms, and then and so on and so on, 100 ohms. And these switches allow us to just to connect a necessary number of 1 ohm resistors in series with necessary number of 10 ohm resistors, in series with necessary number of 100 ohm resistors, and so on. And by this way, we may actually get values from 0 when all the switches connectors stay here, just get a resistance of wire, which may be neglected, or maximal available value when all these switches stay somewhere here, providing a maximal possible resistance of the box. This is a laboratory boxes. This is a view of laboratory boxes which are used for the accurate measurement, for the ethelon measurement. So they are of the high accuracy class. For the lower accuracy class, for the simple measurement, we may use a little bit more cheap devices. So such kind of boxes you may buy in any electronic shop. So they actually allow us to combine whatever resistance in a certain range. For this, here an example. For example, here is one of examples. It's a resistor box. It provides it could model or provide resistances from 1 ohm up to 11.111 megohms with in steps of 1 ohm, and accuracy is about relative error of the set. Resistance will be about 1%. Here is a similar box, but for the capacity. So it provides capacities in the range from 10 picofarad up 11.111 microfarads with a little in steps of 10 picofarads and with accuracy of 5% approximately. One ohm, 2 ohm, 3 ohm, and 4 ohm. This is enough to get whatever value from 1 up to 10. So if we add all these together, 4, 3, 2, and 1, we get 10. So one decade may provide the values from 0 when all the switches is off up to 10 when all switches is on. This design of switches is not very convenient for the working with bridge, because we may not change resistances which such as a bridge in a continuous way. So from 1, 2, 3, 4. So we may switch 1, but we couldn't immediately switch 2 after that. First we have to switch off 1, that's a resistance drop to 0, and then only switch 2. In this way, such type of resistors, they are more convenient in the practical manual measurement because you actually increase the resistances at least within the decades, going from 0, 1, 2, 3, 4, 5 in one movement. Then, of course, when you go to the maximum in one decade, you have to switch to the next, make a next step in the next decade, yeah, but it's more or less more convenient than use such kind of connection. But generally, in all except of easiness of operation, there is no difference between the two devices. They are actually more or less equivalent. So this is more accurate because of higher measurement, higher accuracy class, and used for the more accurate measurement. This is less accurate for the not so important measurement, but generally they are similar. Well, okay, and now let's make a 5-minute break. Okay, okay, let's continue. Is it fine with sound? Do you hear me? Okay, so speaking about the accuracy of the Wheatstone bridge, so how what interesting now is it's actually related to the accuracy. The question is how big or how small resistances we could measure using the Wheatstone bridge. So the why actually we should ask such a question? Because when we measure real resistance of some object, and very often this object may be some kind of sensor, transducer, or maybe indeed we are interested in calibrating of the some kind of reference resistance. No matter what we are measuring, when we measure some certain resistance, so we always has a error, may have a error, which is related, that the resistor of interest is connected to the bridge with some kind of wires. We couldn't connect without wires. And there is some insulation between these points where the resistance is connected. Yes, we should admit that the resistance of the wire is quite small. Usually the resistance of these two wires, which is used to connect our for example, sensor Rx with the resistivity Rx to the bridge, may be less than one hundredth part of the ohm, so of it or 1 ohm. So they are generally small. And the insulation usually is in opposite. It is very high. Usually the insulation exceed 10 in the power of 11 ohm. So it's nearly 100 giga ohm or even 1,000 of giga ohm. Actually, it's order of tera ohms. They're very big. But nevertheless, it appears that even such a small addition or such a big resistance which is connected in a parallel may sometimes affect the measurements. And we consider from such a point of view, let's consider the balance equation. So if we or not, sorry, not a balance equation, let's consider the equivalent resistance of such an actual resistance. So I replace my actual resistor, what I connected here, by an equivalent circuit. So I have the resistance of interest Rx. I have a wire resistance Rv that is added in series, and I have an isolation resistance which is added, or isolation which is added in parallel to all this series connection Rv, Rx, Rv. So if I write down the resistance R1, which is actually now R1 is a resistor which is actually switched between the connections to the bridge here between this and this point. So I write down this equivalent resistance. So we know how to calculate the parallel resistance, total parallel resistance. Yeah. So R isolated times R this series and divided by sum resistance of all the series plus resistance of isolation. So this is a equivalent resistance, actual resistance between these 2 points. The resistance R1, which actually will be counterbalanced, which will be balanced in the bridge. So it independently of what actually is inside the bridge. Yeah, but when we balance the bridge, the bridge will balance not Rx, it will balance this resistance which is connected to the inputs of the bridge. And if this resistance, let's imagine some 10-meter long wire with a small sensor Rx on the end, yeah, so then we have to take into account the isolation between these wires and the resistance of the wires itself. Well, taking into account that the resistance of wires is very small and resistor of the isolation is very high, we just make a little simplification. So we actually divide. I just shorten the R isolation, and when I shorten it, when I divide by R isolation in denominator, I keep only the member where R isolated divided by R isolated, giving me 1, and I keep the member Rx divided by R isolated, because I don't know, I wish to evaluate how the value of Rx may change the accuracy of measurement, and I just neglect this member to Rv divided by R isolation, because if it will be 2 times, it will be actually very, very small. Yeah? So let's imagine 0.01 divided by 10 in the power of 11. So its value will be in the order of 10 in the power of minus 13. So it's very, very small. So we just neglect it, this member. Well, now let's see. Yep. Why we take into account an isolation? Yes? This is your. Okay, let's imagine that we have a sensor and a 10-meter long wire. Yep. So what is it long wire? So I have one wire in isolation attached with another wire with isolation. But the area of this isolation on the 10-meter long wire, it's quite big. So I always have some how to say, some fluid current through the isolation. It's very small, but it is. So isolation as well, there is no ideal isolation in the world at all. It's very good isolation, in very poor isolation. Even if we have a good isolation, we still have some very, very small current flowing from one wire in this cable into another wire. So it's actually the currents that flow through isolation of our wire. Another aspect why we take the isolation, let's imagine the printed circuit board. When we have 2 wires soldered one next to another, yeah? They are isolated by the board itself, but we always have some moisture in the air, and we always have some moisture film on the printed circuit board. And that may cause a very teeny current flowing between these 2 contacts. So the isolation is actually it flows through isolation. So that probably I answer your question. But indeed, it's very big. It's not we are not speaking about even mega. We are not speaking about giga ohms. It's tera ohms. So it's in 10 in the power of 12. So it's very big. If we speak about corresponding currents, let's imagine, so for such a measurement, the voltage is here at 5, it's of order of volts. And we have here a resistance of order of 10 in the power of 12. So we speak about currents in the 10 of the power of minus 12. So we speak about picoampere currents, and even probably smaller. Yeah? The currents are very, very teeny. But for the long wire, it may be a case. We have actually some fluid between 2 wires. Very often we ignore it. And now we're actually looking at if we take into account this isolation, what will be limitation for the measurement of the bridge with the help of the bridge. And let's consider, so actually I write down this R1, so Rx plus resistance of wires, and here is some corrections that actually, because of we have let's say non-infinite insulation resistance. Well, let's consider 2 cases. So one is a case of the very big resistances Rx, and another is a case of very small resistances Rx. So if we take this, we consider this resistor Rx is high, big. I transform a little bit my my formula for R1. So the resistors R1, which is actually inside, will connect it to the bridge. So I put out this Rx, and actually I just neglect this 2 RV because it's very small. It's a resistance of the wire, so I just neglect it. So I put Rx out of this expression, and I got inside the parentheses 1 divided by 1 plus Rx divided by R isolation. I actually may use a Taylor series to transform this expression into expression 1 minus Rx divided by R isolation. So this is a first term of the transformation of this ratio using the Taylor series. So the first term of Taylor series. So it's actually the corresponding expression is 1 divided by 1 plus x, where x is very small. Here, obviously, x, even for the big x, is quite small comparing with the isolation. And I just use here this Taylor series. So I may roughly replace all this equation with this equation for the big Rx. And then I see that the value with the bridge will be measured by the bridge, R1, will be Rx, will be a little bit less than Rx, and the relative difference is just this Rx divided by R isolated. If I set a goal to have a measurement, to have this difference between the actually measured R1, and between measured R1 and actual value of Rx to be less than 0.1%, actually what I have to require, that the ratio Rx divided by R isolation will be not more than 0.0001, 1/1000th. In fact, I speak about 0.1%, but it is actually 1/1000th without percent. So the ratio is equal to 1/1000th. So if I require that this ratio should be at least 1/1000th and less, so I will get what will be the maximal Rx, taking the poorest situation with the smallest isolation of 10 in the power of 11 plus 3 order from this 1/1000th, I get that resistance Rx should be less than 10 in the power of 8. But it's actually not so bad. We speak about 10 in the power of 8, it's 100 mega ohm. So we actually may measure with 0.1 giga ohm with this bridge, and the accuracy of measurement will be better, will be more or less within the range of 0.1%, so not worse than 1.1%. So this accuracy because of this effect of the wire and isolation itself. So we may easily measure with this bridge voltage, not voltages, but we may easily measure the resistances with up to 100 mega ohms. Another opposite side, the opposite side when we have a very small Rx. So if I have a very small Rx, I actually, so what I do here. So I should remember what actually I do here. For the very smallest Rx. So the small Rx I probably neglect. Well, what I'm neglecting here? RV divided by Rx. Yes. Yeah, okay, understand that. For the small Rx, I just neglect for this member, Rx divided by R isolation. So it's very small. It's small. It's less than 10 in the power of minus 11. And then I just move out Rx out of this sum in front. So I get that R1 will be approximately Rx plus 1 divided by 2 RV divided by Rx. So the same, the measured resistance will differ from the actual resistance by this relative member, and the same. So this is my relative measurement error, the RV divided by Rx. And one more, I require that this error should be less than 0.01%, and from this it means that this ratio to RV divided by Rx should be less than 0.1% or 1/1000th. And from this, comparing with the typical value of wire resistances, I get that the lower range for the accurate measurement with the bridge will be approximately 10 ohms. So it's difficult to measure with the resistances which are not difficult. It will not be accurate measurement for resistances that is less than 10 ohms. So this is the range of the bridge, Winston bridge measurements between 10 ohms and 100 megohms approximately. For practical reasons, actually not for a practical reason, but in our field, in medical engineering or in a measurements, we often are interested in a measurement of small resistances, because very often the thermal, there's some kind of sensors which transform measured value into resistance have a very low resistances. As an example, I may, for instance, if there is such a devices, they are named bolometers. So bolometers, it's a teeny film, thin film resistors which are covered with that have a blackened surface. They usually are covered into carbon, and they actually absorb heat because they are very black, and change the resistance because of heating. So they are used as a very accurate and well calibrated sensors for the radiation measurement, not not ionizing, but for different kind of non-ionizing. So it's light, actually ionizing too. So they could measure the intensity of light, they could measure intensity of infrared light, and they are very teeny, very small, usually made of platinum, covered with a porous platinum or special porous carbon to be as black as possible, but because of small sizes, they have a very small resistance. So in a measurement device, we very often are interested in the measuring of very small resistance. So we consider now the two examples how to measure how to extend the bridge measurement range into the smallest resistances. One of such a method is to use so-called four-terminal connection. So in fact, we actually use the same Wheatstone bridge as a base, but now we connect our resistor, what we are going to measure, not with the two wires like here, but we connect it with the four wires. So two wires from one side, what does it mean connect with the four wires? So these wires are connected as close as possible to the resistor itself, just physically. So if it's a bolometer, as I said, a thin film. So we attach these wires just exactly to each of the bolometer, and from one side and from another, the two wires. And now these four wires are used to connect this Rx into the bridge in such a way. So let's look how we do connect it. So the power to the bridge comes through one of these wires. Then one of the arms of the bridge is made of the resistor Rx itself. The second arm is made of the series connection of the wire which comes to resistor and Rx and R3. The third arm is made by the resistor R4 of the wire number 4 and resistor R2 of the bridge. And the bridge itself is made of the resistor in series, the resistor R of the third wire connected to the resistance to our sensor and voltmeter, which connected to the bridge. And only resistor R4 is exactly inside the bridge. So actually, if we look at this as our bridge, it's some box with the contacts, then here we get that the contacts are actually all the bridge. If we compare with this design, so here we have a bridge in a box and two contacts. So all the bridge is except of our resistor Rx, and these contacts are inside the box. But here, good part of the elements of the bridge is out of the box and is in the cable which comes to our resistor Rx. So this type of connection. So in fact, what changed here in our by the way, this type of connection, of four-terminal connection, is called Kelvin bridge. So it's invented by Kelvin, the Kelvin bridge. And let's see what will be the equilibrium rules now. So actually, what changed? So these are this wire. It's actually absolutely it is not related to the balance of the bridge. It's just a wire which used to provide a power to the bridge. Yeah, voltage to how to say, no, power voltage to the bridge. What changed actually? This one doesn't play any role because in a balance the current through this branch will be zero. The bridge itself will be zero, so this resistance doesn't play any role in the balanced state. So what actually changes is the resistor R3 should be replaced by R3 plus the wire resistance RV2, and resistor R2 should be replaced by resistance of R2 plus resistor of the wire 4. So, as a result, when I calculate the balance, use the balance equation, so it's actually a balance equation just in a little bit transformed form. So it's not an R1 divided by R2 equal to R3 divided by R4, but I just express it R1 over the other parameters of the bridge. So I may transform it. I may transform it, and when I transform it, I get this relationship for the balanced bridge. So what I see, so this actually part is equal to this R1 equal to R2 R3 divided R4 if I wouldn't look on this part in parentheses. So all this part is actually equal to the original equation, original balance equation of the bridge, but it's a little bit distorted. So here is a distortion which is related to the existence of the resistance RV1 and RV2 and RV4 of this wire resistance. If I look at I'll always may select R3 and R2 big enough to make the ratio between lead wire resistance and resistance R3 or R4, R2 less than even 0.01%, even of 1,000th part. And if I set such a rule, such a requirement, so, and bearing in mind that normal convenient value, for instance, for R3, R2, maybe about 1 kilo ohm, and the resistance of wires is about 0.01 ohm, I found that in such a connection I may accurately measure resistances up to 10 in the power of minus 4. So in fact, it means that I may measure really a resistance of piece of platinum foil. Yeah. And this is even not a maximal, not a minimal range what we could reach for the measurement of resistances. So for our purpose, if you speak about measurement in medicine and the related fields, generally the 4-terminal connection is absolutely enough. But in some other technical fields, for instance, when we try to explore some conductors and really are interested in conductivity of conductors, and resistance is very small, even 10 in the power of minus 4 in actually micro ohms could not be enough. So we probably need even less resistances, be able to measure less resistance. For this one could use such a device as so-called double bridge. It's just for information. We never use this in future. And just for your information, there is such a device. So the double bridge actually allow to measure resistances from up to 10 in the power of minus 8. So we even speak about 10 nano ohms, 10 in the power of minus 8 if it's 10 nano ohms. So double bridge may measure a very small resistances. There is only requirement is the design of the bridge. So if we try to calculate the balance condition for the bridge, so when we have this voltage V here equal to 0, we found this equation. So the unknown resistance Rx should be related with the known resistance R0 and all these R1, 3, 4, and 2 in such a way. Technically, very often the R1 and R3 taken the same, and R4 and R2 taken the same. So, and then we balance this bridge, and when this is balanced, so when it's balanced, so we get actually that Rx is equal to R0 divided by this ratio between R1 and R2, but this balance will be enforced if the resistance R is as close to 0 as possible. So very often these 2 points, they just connect together using very, very big diameter conductor. Very short with a very big diameter. So this R is actually the resistivity of very big diameter, very well good, very short, usually copper conductor. And double bridge is so accurate that it's actually, we actually should take into account the thermo ADS, thermoelectromotive force that may appear in any connection when we attach two different type of wires, I mean made from different materials. So if I have this R copper, I may have copper here, but probably here I have some tin covered contacts and so on. So everywhere where the two different materials are in contact, the thermo ADS the thermoelectromotive force may appear. And this double bridge usually is operated in usually it's a two measurement I taken. One, we connect the polarity plus minus to the power of the bridge, to power the bridge. And then we make measurement, write down the result, and then we turn the polarity in opposite direction, add here plus, here minus, so to reverse the current flows here, and make a second measurement. And as a result, we take the average between these two measurements. So generally, if our Kelvin bridge, for instance, contain a different materials, it may contain a different materials. Generally, the thermoelectromotive force may be the source of the error in usual bridges bridges too. So for the Kelvin bridge, sometimes, at least at the stage of development, it's quite useful to check whether the measurement results differs if we change the polarity. And if so, if it differs, it means that we have here in a bridge somewhere a high source of thermoelectromotive force, and because of, as I said, connection of two different metals together in one contact. And then either we take this error into account, so by some kind of applying some correction, or we just made a measurement, changing the polarity. And finally, some comment, because it's just going to finish now, some comment about automated bridge. Generally, when we look at what happens if the bridge is not in balance, if I look at this bridge, which is not in balance, especially the bridge with the voltage. So if it's not in balance, we have some voltage between points 1 and 2. And if we start to balance this bridge, for instance, and R3 is still less than Rx measured, so it means that probably this voltage will be higher than this, and the voltage, so this voltage will be higher than this with one polarity. Then we continue to balance, and let's imagine that we overbalance the bridge. So we come to balance and continue to increase R3. If we continue to increase R3, the bridge will go out of balance once more, but now this voltage will be less than this one. So independently of we are before the balance, or we are after already after the balance, we will have a different polarity in this voltage between points 1 and 2. It's switched. And we may use this voltage. We may use this voltage to control some electromechanical device which try to balance the bridge. So here is an actually scheme. It's not a entirely Kelvin bridge, but it's Kelvin-like bridge. So we actually use a 3-probe connection. You know? We use a 3-probe connection when only one of the wires included in series with Rx. So this is somewhat like an example. So we have a voltage between points 1 and 2 that is not equal to 0 when bridge is out of balance, is not balanced. And we use this, take this voltage, we apply some may use this voltage as the input of some amplifier, and the instrumental amplifier in a very good solution here, because it takes a difference between two voltages. So we take some differential or instrumental amplifier to measure this difference, and we use the output signal of the amplifier to control the motor. So if there is a difference, so we have a signal on the output, we may use different kind of motor control. It may, in the simplest way, is just if the output voltage is more than some certain small level, we switch the motor on. If it's lower than certain negative level, we switch the motor with the reversed polarity for motor to turn in another direction. And when other case, maybe we just use this amplified voltage and power this motor via a buffer, some kind of buffer, yeah, buffer or a meter follower, to just control the motor automatically. So if we have a positive voltage on the output, the motor will rotate, DC motor will rotate in one direction. If we have a negative in respect to zero, it rotates in the reverse direction. So anyway, so this motor actually control the alternating resistor here, and change this resistance, hereby changing the balance of the tilt of the bridge. So if we connect all correctly, so if our direction of rotation is corresponds with actually the direction is of rotation should be adjusted in such a way that when I have the rotation of the bridge under the control of this difference signal of this difference should lead to the reduction of the difference. If I mix the direction, if it will be if I mix the direction, if I switch the direction of rotation to opposite, I actually get that my bridge never come to the balance, because the biggest this balance will be, the biggest this voltage will be, the motor will move or regulate the resistor in such directions that this difference become even more bigger and bigger. So we have to provide the negative feedback. Yeah, so the motion, the working of the motor should change the resistors here in such a way that this reduces the difference between points 1 and 2. For this I need a motor which is connected to the resistor, and here is an example of different kinds, so-called motor potentiometers. They very often are mounted together. So actually this is a motor which turns the multiple turn potentiometer. Here is a motor that turns the potentiometer. So it is here. Here is a motor that turns a potentiometer and simultaneously moves using this this belt, the belt gear, moves this cartridge back and forth. So if we attach a pen to this cartridge, so we get a plotter which draw us a line, and we have to pull the paper, and we get a recorder. So this potentiometer assembled together with a motor, better to say motors assembled together with a potentiometer, is a center of the automated bridge. Nowadays, it may be already that this resistor is controlled for the digital bridges. That this resistance may be controlled by the digital to analog converters. There is special type of digital to analog converters which accept a digital number and change their resistance. So we may use digital to analog converter to balance the bridge. But nevertheless, the principle is the same. In this way, we just use this input from the bridge, measure it digitize it, convert it to the digital form, provide this as input data for the processor. The processor actually provides some control algorithms that change this R to get this to change this resistance, to get this feedback, negative feedback, to reduce this voltage. So this is the idea of automated bridge. And for today, we actually, with this I actually end for today. Well, and we meet next week. Okay, if any question, please don't hesitate to ask. Okay, if there is no question, so thank you for attention and let's meet next week.
Thank you very much. Goodbye.
Bye bye.